If you took 10 academic, you would have been exposed to exponential functions, but very briefly, and the 10 applieds haven't, so I'm going to treat this like it's new. We are introducing you now to the exponential function. So in grade 9, your main function was linear function. In grade 10, your main function was the quadratic, and now in grade 11, your main function is the exponential function. So I'm going to show you in this video how to graph an exponential function, and there's no magical way to do this other than really just making a table of values. Now, an exponential function has a base and the x is in the exponent. That's how you make an exponential function. So to graph it, you're going to make a table of values, and I would suggest starting when x is equal to 0. So when x is equal to 0, you're going to take that value and you're going to substitute it in for x. So that means 2 to the exponent 0 is equal to 1. And if x is equal to 1, 2 to the exponent 1 is equal to 2. If x is 2, 2 to the exponent 2 is equal to 4. If x is equal to 3, 2 to the exponent 3 is equal to 8. And if x is equal to 4, 2 to the exponent 4 is equal to 16. So if we were to plot these points, you have a point at 0, 1, 1, 2, 2, 4, 3, 8, 4, 16, 5, 32. Next one would be 64. And the right side of the graph would look like this. Kind of looks like the right half of a parabola, but let's see what happens on the left side. So when x is equal to -1, 2 to the -1, remember a negative exponent flips the base upside down, so that is equal to either 1/2 or it's equal to 0.5 if you wanted to make it a decimal. 2 to the -2 is 1 over 2 squared. So that would either be 1 over 4 or 0.25. And if x was 3, 2 to the -3 would be 1 over 2 to the 3, which is 1 over 8 or 0.125. So if we were to plot these, when x is -1, let me even zoom in here. When x is -1, y is 1/2. When x is -2, y is 1/4. When x is -3, y is 1/8. And the next one would be 1 over 16. Next one would be 1 over 32, then 1 over 64, then 1 over 128. And basically what happens is the line keeps getting, or the value of y keeps getting smaller and smaller and smaller as we move to the left. Just keeps getting smaller and smaller and smaller. But the important thing is that it never actually gets to 0, because there's no number that you could substitute in. If you have 2 to the exponent x, there's no number that you could substitute in for x and make 0. Now the problem is when we start graphing things like 1 over 8 or 1 over 16 or 1 over 32, it's hard to really make it look like it's at 1 over 16 or 1 over 32 without it either looking like it's touching 0 or making it look like it's too high. So what we do is we graph what is called an asymptote. And an asymptote is really just a dotted line, and it goes along the x-axis. So you would draw this as a dotted line. You would use a ruler, although I don't have a ruler on here to use, so it doesn't look like I'm using a ruler, but the equation is y equals 0 because it's going right along the x-axis. And what that represents is the fact that the graph looks like it's touching 0, but it's actually not touching 0. So on one side, the graph looks like it's making a parabola, but on the other side, it is approaching the x-axis and getting really close to it without touching it. So this dotted line here is what we call an asymptote. So an asymptote is a line that a graph gets really, really close to but doesn't actually touch it. So the point of drawing the asymptote is to show that we draw this as best as we can. This green graph looks like it's approaching 0, but it's not actually touching 0. So it is important that you actually do graph that asymptote. So in order to graph these exponential functions, what you would do is you would plot the y-intercept at 0, 1, because when you substitute in 0 for x, anything to the exponent 0 is equal to 1. Your asymptote would be at y equals 0. And you'd have to make a table of values. Now you could do it mentally or you can do it on paper, like here. So for instance, if we were going to draw, this one here is y equals 2 to the x. If we wanted to graph y equals 3 to the x, then once again you start when x is equal to 0. And you could do this in your head. You don't have to make the table of values. You can actually just do it in your head. When x is equal to 0, 3 to the 0 is 1, so there's your y-intercept. When x is equal to 1, 3 to the 1 is equal to 3. When x is equal to 2, 3 to the 2 is equal to 9. When x is equal to 3, 3 to the 3 is equal to 27. And you just graph as much as you can until you run out of room. There's no point in doing x equals. And then you would just do your best to draw a curve through those points. And then on the negative side, when x is equal to -1, 3 to the -1 is 1/3, 1 over 3 to the 1. And that is approximately equal to 0.3. When x is equal to -2, 3 to the -2 is 1 over 3 squared, which is 1 over 9, and that's approximately equal to 0.1. Those things you can just find out on your calculator. So on the left side, when x is 1, you've got 1/3. When x is -2, you've got 0.1. So on this side, you're just going to get closer and closer to 0 without actually touching it. And that's how you graph exponential functions. Now, if you remember, linear functions had equal first differences. Quadratic functions had equal second differences. That does not mean that exponential functions have equal third differences. What they have are equal ratios. And the ratios are found similar to how first differences are found, but instead of subtracting the values, you're going to divide the values of y. So instead of taking 16 and subtract 8, we're going to take 16 and divide it by 8, and that gives you 2. The next one, 8 divided by 4 is 2. The next one, 4 divided by 2 is 2. And it ends up that they're all equal to 2. And that 2 is not a coincidence. That 2 is the same as the base of the function. So the base of the exponential function is the same as the common ratio. And all this really is saying is that your y values are multiplying by 2 each time. So whatever the base is, your y values are multiplying by 2 each time. If you go down, they're dividing by 2 each time if you go up. Next, we're going to look at some properties. So in this case, the y-intercept is at 0, 1. And all of these, when they're in this form where it's just a base with an exponent of x, the y-intercept will always be 1, because whenever you substitute 1 in for x, any base with an exponent of 0 is equal to 1. If you take 11u and you work on the exponential functions unit, they will start doing shifts and translations, the same thing, stretches, compressions, reflections, so the y-intercept may change, but for what we're going to do in this course, the y-intercept is 1. The common ratio in this example is 2. It's the same as the base. The domain is XER because our graph will go all the way to the left and all the way to the right. Our range. Now, it looks like it goes down as far as 0, but remember the asymptote means it doesn't actually touch 0, so we're just going to say y is greater than 0, not greater than or equal to 0. But the graph continues all the way up to, it would just keep going, so there's no upper bound. Our lower bound is 0, but it's not greater than or equal to 0, it's just greater than 0. And then YER, of course, just means that the graph is continuous, there's no breaks. Y could be any number that is greater than 0. This graph is increasing. Now what we're going to look at is a graph where the base is a fraction. So if it doesn't show up on your sheet, this is 1/2 to the x. So there's basically 4 things we are looking for when you're graphing these. And as we said before, the y-intercept is always at 1 because anything to the exponent 0 is equal to 1. The other thing to know is that you're always going to have that asymptote at y equals 0. So that is the horizontal line that the graph will never end up touching. Always make sure you label it. And then you can either make a mental table of values or you can write it out. So if x is 1, 1/2 to the 1 is 1/2, which is the same as 0.5. So that's at 0.5. 1/2 to the 2, that's equal to 1/4, which is also 0.25. Again, this is the whole point of the asymptote, is that it's hard to plot these points without actually making it look like it's touching 0. And then 1/2 to the 3 is 1/8, which is 0.125. Okay. And I'll just leave the next one blank because it's pretty much hard to plot those. So this is the part that looks like, again, it looks like it's horizontal, but it's not. It's just decreasing very, very slowly and approaching 0, but not actually touching 0. Then on the negative side, if you have 1/2 to the -1, remember negative exponents mean that you flip the exponent upside down. So that would be 2 to the 1, which is just 2. So at -1, your y value is 2. When x is -2, flip the 2 upside down, so that's equal to 2 squared, which is 4. And if x is -3, 1/2 to the -3, flip 1/2 upside down to make 2. So that's 2 to the exponent 3, which is 8. That looks like a 23. So it's 2 to the exponent 3, which is 8. The next one, if it was 2 to the -4, the next one would be 16. And then the next one would be 32. So this side would go up And you don't have to go off the grid, but I'm just going to go off the grid here for a second, because what I want to show you is take a look at the green graph, which is 2 to the x, and the red graph, which is half to the x, and take a look at the numbers. So 2, 4, 8, 16 on the positive values of x. On the negative values of x here, it's 2, 4, 8. The next one, it would have been 16. On the negatives, 0.5, 0.25, 0.125. Here on the positives, 0.5, 0.25, 0.125. So this green graph and this red graph, these are a mirrored image of each other. They're really just reflections over the over the y-axis. So now to finish this off, we're going to have, again, the ratios. So the ratios between this, if you took 0.125 and divide it by 0.25, in your calculator you would get 0.5, which is the same as 1/2. And remember, that's the base, and the base is equal to the common ratio. So because this is exponential, all of the ratios will be the same. So 0.25 divided by 0.5 is 0.5, which is the same as 1/2. 0.5 divided by 1 is 0.5, which is 1/2. And they're all equal to 1/2. And your properties, the y-intercept again is at 0, 1. The common ratio is 1/2. It's the same as the base. Domain, remember, it goes all the way to the left, all the way to the right, so that's XCR. The range, the lower bound looks like it's 0, but it's not actually touching 0, so it's just y is greater than 0. There's no upper bound because it goes up forever. And then YER, and this one is decreasing. So the difference between these two is when the base is a number that is bigger than 1, then it is an increasing graph. And if your base is less than 1, it's a decreasing graph. So we're just going to summarize all of that up in this section here. So you've got two cases to look at. Your graph could be increasing or it could be decreasing. It is increasing if the base is bigger than 1, and it is decreasing if the base is less than 1. But we also say that the base has to be greater than 0 because you won't have any bases that are 0 or negative. So your bases will always be positive values, and it's just whether it's bigger than 1 or less than 1 if it's increasing or decreasing. The y-intercept will always be at 0, 1. The common ratio will be whatever the base is. The domain will always be XER because the graph will be going to the left and to the right. The range, as long as your graph is in this form, or so your equation is in this form, and we don't have anything in the x, in the exponent, like we don't have a to the x plus 1 or anything like that, then the range is y is greater than 0, YER. The two graphs are reflections over the y-axis. And as we saw over here, if that base is 2 and that base is 3, if you increase the base, what happens is that the graph grows quicker, so the increase looks steeper. So as A increases, the graph increases or decreases. quicker.